In this module, we apply frequency response techniques to the design of controllers. Previously, we introduced frequency response methods as a means for analysis. In this module, we will apply these techniques to the design of controllers. Since what we ultimately want to achieve is some sort of response of the system as a function of time, i.e. in the time domain, the first thing that we then need to do is to understand the relationship between a system's time response and its frequency response. Once we've done that, we will then show how to employ Bode plots for the design of controllers, and then finally we will discuss some other goals of a controller, including robustness and optimality. So when we design controllers, we are going to use the open loop frequency response. So what we want to be able to do is to connect aspects of the system's open loop frequency response to its closed loop time response. So take a look at an open loop Bode plot, for example, and understand how it relates to the closed loop step response. The reason why we want to use the open loop frequency response for design will be explained shortly. So first, let's just try and use our intuition of frequency response to connect the two, and then this will be summarized on the subsequent slide. So let's first think about steady state error. For a type 0 system and step reference, E steady state depends on the DC gain, and it has some sort of form like this. So recalling this sort of expression which we derived earlier in a previous module, think about what aspect of the frequency response plot would tell us about a system's steady state error. What the steady state error is for a step input, for example. DC gain corresponds to a constant input, and a constant input basically has a very small frequency, a frequency of 0, if you will. And so if we look at a system's frequency response, small frequencies are to the left on the Bode plot. So this region over here gives an indication of a system's DC gain, and in turn tells us about a system's steady state performance. So say at steady state. Now let's think about what might tell us about a system's speed of response. For example, its peak time, how quickly it rises or reacts. So looking at the frequency response plot, what we can see is that most typical systems, they can track slowly moving inputs well. So at low frequencies, a system tends to have a magnitude that's 0 dBs or greater, meaning you put in a sinusoidal input and the output is either equal in magnitude or it's amplified. As you make the input faster and faster, have a higher frequency, oftentimes the system can't keep up. And so what it does is it starts to attenuate the input. So you could sort of imagine, let's say we had a first order system. And so if we put in a step input and then we turn the step off, and then we turn the step on, and then we turn the step off. If we do it at a very slow frequency, the system has a lot of time to react, and so it can get very close to its steady state value. But if we're switching that step input on and off very quickly, then the system doesn't have very much time to react, and you get in essence a very small amplitude output. And so that's typical. So if our system is fast, it can track fast changing inputs well, but if our system is slow, then it can't react very quickly and the output ends up having a very small amplitude. So out here, high frequencies tell us about speed. How fast of an input our system can track tells us the speed. If the system can track a very high frequency sinusoid, then it's a fast system. If it can't, then it's slow. Now let's think about what would relate to overshoot or oscillation. So one thing that you might recognize is basically how big a system's resonance is. If it has a large resonance, that indicates that the system will have more overshoot. Furthermore, if a system overshoots a lot, it tends to indicate that it's not very stable. And so we can also look at stability margins, in particular phase margin. So these are three sort of basic things or areas to look at to tell us about steady state behavior, speed of response, and overshoot/stability. And they're further summarized on the next slide. Okay. So in terms of steady state performance, we need to look at low frequencies because a constant input corresponds to a frequency of basically 0. So larger gain at DC indicates reduced steady state error. And this is true no matter the type of the system. But if we had a type 0 system, then the slope at low frequencies is flat, and the DC gain is recognized by the magnitude at those low frequencies. If we have a type 1 or a type 2 system, the magnitude at low frequencies won't be flat, it'll be sloped. And the slope will indicate the system type. So if we have a slope that decays at 20 dBs per decade, then that tells us we have a type 1 system, we have one integrator. If it decays at minus 40 dBs per decade, then we have two integrators, we're a type 2 system. So that also indicates the sort of steady state behavior of the system. And even if we had a type 1 system, if it was raised, if the magnitude at which the plot crossed 1 radian per second, for example, was higher, then that would indicate that the system could track a ramp with less error. So larger DC gain or larger magnitude at low frequencies in general indicates steady state performance. In terms of transient performance, a smaller resonant peak and a larger phase margin indicates smaller overshoot and that the system is more stable. Speed of response is indicated by a larger gain crossover frequency. So gain crossover frequency is the frequency at which the magnitude goes from above 0 dBs to below 0 dBs. So that's basically the frequency at which the system goes from amplifying an input to attenuating an input. And a system attenuating an input means basically that it can't keep up, that it's not fast enough to track an input of that speed. And so gain crossover frequency is a good indication of a system's speed.